Hello everyone, my name's Simone Winkler. I am an assistant professor at Cornell Medicine, and today I'd like to be talking about MRI safety, which is an important aspect in MRI because there's tissue heating that happens. And so we have a prediction methodology in this presentation, and we present a little feasibility study for our early stage work. I'd like to start off by introducing MRI and specifically ultra-high field MRI a little bit because most people don't know exactly how it works, and that's really crucial to the understanding of this talk. Then I'll talk about what exactly we mean by MR safety. And then, I'll show you our deep learning approach to predict tissue heating. I'll follow up by showing results, and then because this is early stage work, I would also love to discuss some, potential future work that could be used to really use this in vivo in the clinic. All right, so let's get to the MRI basics. I think a lot of you might know this, but it's really important to this talk, so I'd like to, repeat some of the basics. So MRI, it's actually created from really, really small magnetic fields that are existing in the body. So isotopes in the body that have an odd number of protons possess a non-zero spin, and because that means that they're moving electrons, there are these small magnetic fields. And that's really what we excite and measure in MRI. Now, you could do that with several isotopes in the body that have these characteristics, but really the most widely used one is hydrogen because it has very high tissue water content. Now, what do you do in order to get an MRI signal? Well, the first step is that you align all of the spins to either be spin up or spin down by using an external static magnetic field B0. That field is usually really high. It's like 3 Tesla clinically right now, or 7 Tesla, which is, or higher, which is called ultra high field MRI. Those are usually only used in research with some limited clinical applications already. What's important about this is by doing that, all of these spins will start to precess like a spinning top at the Larmor frequency. So that's a typical frequency related to each field strength. And now in order to put in and take out energy coupled to this system, you'll need to use a time-varying magnetic field at exactly this Larmor frequency in step 2. So you perturb this situation with this field and you excite the spins that way, and then when you turn it off, it relaxes back, and if you quickly measure, you can measure the magnetization of the protons. So basically, the key ingredient to this whole MR signal is this time-varying magnetic field at exactly the Larmor frequency. So remember that part. That's going to be important. Now, why do we want higher field strength? Isn't 1.5 Tesla enough, or even 0.1? Well, the answer is that you get a lot higher sensitivity, or actually signal-to-noise ratio, as you go up in field strength, because if you look at it from a quantum mechanics standpoint, the energy gap increases. You can use that, as shown here in this picture, for better resolution. Or, you can use it for other things as well, faster imaging and so on. But the real takeaway from this slide is something we need to consider. It's good for the image to go up in field strength, but what also happens is that the Larmor frequency is directly proportional to the field strength. So the frequency goes up. So if you go to 7 Tesla, for example, you're already in the range of, 300 megahertz, which, is in a ballpark where electromagnetic effects start to be important. I know, of course, microwave engineers find 300 megahertz very low, but in dimensions compared to the body size, that is, that is sizable. All right. So let's talk about safety now that we have covered what we need for an MR signal. So basically, this MR signal is based on that time-varying magnetic field. Remember how I said to think about and remember that. And now all the MTT people in the crowd will know that this time-varying magnetic field is not going to exist without an electric field, right? So yeah, this means in very short words that the transmit signal is not just magnetic, it's electromagnetic. So what does that mean? Electric fields can be good or bad, but in this case, they're actually bad because they cause tissues to heat. It's also the principle of a microwave oven. And, you know, that means there need to be metrics for safety standards. And what's been adopted throughout the last few decades has been the specific absorption rate, also abbreviated as SAR. This comes from the cell phone industry, so you know we're using kind of the same thing here. Some people don't really like that idea, and they would prefer to see temperature as the metric, which is implemented in some standards. But let's focus on SAR for this talk. So let's look at the regulations for SAR. So one regulation looks at the same regulation, but one aspect of the regulation looks at the global SAR, which means the RF power deposition over the entire anatomy of interest. So in a brain scan, that would be the head, and then you know, knee scan, that would be the leg, and so on. Or I guess that's more complicated, but take what I said just for this slide. Okay, and that can be measured, but then you also have local SAR variations, and what's important here is that you can have these hotspots as you see in this image. So you know you can have spots where it gets really hot, and you sometimes don't know that this happens. So that's really hard to predict. That cannot be measured yet, but it's crucial because those hotspots can be so much higher than the average or global SAR. All right. What are the implications of field strength on SAR? At low field MRI, the wavelength is longer, right? Because the Larmor frequency is lower. So the SAR hotspots, I mean, I wouldn't say no SAR hotspots, but to simplify it, the SAR hotspots are definitely not as closely together, right? But then when you go to higher field MRI, there are several things that happen. One is that SAR is a power measure. So it increases with the square of the static magnetic field strength. So that's already a big issue. But then in addition, the wavelength is shorter, so you get the hotspots, right, as seen in this image below. So that's a brain SAR image at 7 Tesla, which is almost 300 megahertz. And now in addition, what's really, you know, the really big trouble is that this varies so much. So between patients, between different RF coils, or if you move a bit, this local SAR pattern really changes. And it gets very hard to predict. It's like, you know, you can't just run one simulation and have all the people covered. It really changes. The third one I'm going to leave out. It's just in case you use multiple coils. You might cause constructive interference. So here is an example of what SAR looks like. At 3 Tesla here, we look at a body image, and you can see that the wavelength is actually 26 centimeters. So even though that's a lower field strength, over the width of the body, you already do see some wave effects. So, you know, it's higher for the arms and then lower in the middle, that kind of thing. And then for 7 Tesla, where we look at the brain in this image, the wavelength becomes 11 centimeters. So of course, that's close to the brain dimensions, and so you're going to have hotspots in the brain at 7T. You know, if for example, if you did a brain at 3T, maybe you wouldn't see so many things happening. Now, what do we do? Well, there's no in vivo real-time SAR monitoring capability yet. That doesn't exist. There are all kinds of workarounds with stored databases and so on and forth. It's crucial because, you know, you really need to know if you cause very hot local areas, you know, for safety. But of course, the other thing is, what people do nowadays is just they introduce these huge margins just to be safe. They transmit a lot less signal than they they think they can, just so they're on the safe side. And so, if you're able to predict SAR better, then you can also use more signal and get a better image. All right, so in this work, we're proposing to use deep learning to predict SAR and tissue heating. So what we do here is we train a 2D UNet, and the input is an anatomical image, and the output is a SAR image. This has 3 layers of depth and relocalization and some other parameters that are mentioned here. I'll go into more detail on the data generation, but this is in principle the deep learning network that we use. It takes 6 epochs to train it with ADAM and 30 for SGD. Now, everybody who knows deep learning knows that the data preparation is really the most important aspect of the work. So let me go into a bit of detail of what I did here. I generated data for both 3 Tesla and 7 Tesla. And for the 3 Tesla, we know that the SAR varies over body dimensions, remember 26 centimeters. So I used a body coil with a male body model. And for 7 Tesla, we know that the brain dimensions are already an issue, so I used a brain simulation. And so then the input of the training network is the anatomical data. As you remember, in the end, what we want here is an MRI image, but for this first feasibility study, we just used an image that looks kind of like an MRI image. So I kind of just used the voxel slices of this model, just so it's easy to have the same geometry in input and output. And in the future, that will change. The other thing I did was to multiply this anatomical image with the magnetic field of the coil. And what that does is it encodes the position a little bit, right? So you can see that the coil was kind of covering this part of the body. That way, it's kind of an easy way to have a little bit of position information in there. And then the output was simply SAR simulations of these 2 models, right? And then we averaged the SAR over 1 gram of tissue, which is the US standard. Now, we moved the body model around in the coil to cover different positions. So, I get some variation as well, 224 for Duke and 175 for Ella at 70. And all over that gave us about 23,000 slices to train on. Now, here are some results. This is the 3T results. I'm showing 2 positions here. So if you look at the right, you have the input anatomical image, and then the simulated SAR, right? So this is basically what the ground truth is, because that's what the SAR simulation looked like. And then we predict the SAR using 2 different optimizers, and you can see it's getting there. The ADAM optimizer is a bit better here at the hand, and overall, it's looking fairly good. But if we look at this other example, position 1, where actually more of the shoulders and the head are in the coil, you have the input here and then the SAR simulated ground truth. And then you have these predicted SAR patterns that have really those hotspots very nicely depicted. So you have an error of, about 6%, 7% in both cases. And that's, for a first result, that's pretty good. Of course, we want to, refine this a lot and move on from here. The second case was the 70, so the brain image. This one was a little bit harder. It got blurrier. As you can see, input image simulated ground truth. This is SGD and this is ADAM. But both of them, even though it's blurry, show this hotspot at the top of the head, and also this one, probably the ventricles or something like that. I'm not a doctor. And in the end, it doesn't really matter how blurry it is. It matters that it shows the temperatures and the peak locations. Same for a different position. You get a hotspot here for the SAR around the, I don't know, maybe the thyroid or something, and you get those nicely depicted here along with the hotspot in the neck. The errors are 6% and maximum of 10%, which is working out nicely for our first study as well. Okay, so now let's move on to how to use that in an actual MRI exam. So what you would do here is you'd acquire an input image and then register it into your software and predict the SAR from your deep learning. And then you can calculate the peak local SAR from that and calculate how much transmit power you can use in your scan. One thing we'd also like to do is use a larger catalog for training, and the IDIS Foundation has all these really cool models. So there are like, I don't know, 27 or something. So we could make a really, really large network of models and physicians. There are pregnant ladies and obese people and kids, babies, and all kinds of things. So if we made a really large catalog for training, we'd cover a very wide array of the population for this work. All right, so in conclusion, we learned that the Maxwell equations dictate that there is an electric field in MRI, and these electric fields cause local tissue heating, and that's really hard to predict. And so this work focuses on proposing a deep learning algorithm that is capable of predicting local tissue heating. Thank you very much. I'd like to thank my collaborators and acknowledge volunteers.